So this is the pre-lab introduction video for the foundation physical experiment, which is about the partitioning of natural products. Now, this experiment basically comes down to some really fundamental thermodynamics. So I'm going to start and get you to think about what makes something mix with water and what makes something not mix with water. And ultimately that always comes down to the most important law of thermodynamics, which is the Gibbs equation. Delta G is equal to delta H minus T delta S. For a reaction to be spontaneous, for any process to be spontaneous, then delta G has to be negative, which means that we're balancing two things. Delta H, the enthalpy change for the reaction, which is really the entropy of the surroundings, and minus T delta S, the entropy of the reaction and the thermodynamic temperature, because it's obvious that as the temperature increases, we're increasing the total entropy. Now, if I think about water as a liquid, we know that there are all sorts of bonds in water. We have the London dispersion forces and we have dipole interactions, but we have a very, very strong hydrogen bonding network. If I try and mix octanol with water, what happens is the octanol disrupts this hydrogen bonding network. Now this affects delta H. The more bonds I form, the more energy that is released as heat. This is my enthalpy of my reaction. If I put octanol in and disrupt that hydrogen bonding network, I'm generating fewer bonds and therefore I'm making the contribution from delta H be less negative. Consequently, delta G is less likely to be negative and it's less likely to be spontaneous. And what we tend to know happens when we mix oil and water is the two liquids don't mix. We get a phase boundary between them. And in the case of octanol and water, we have a distinct phase boundary. Now that doesn't mean that there's not a tiny little bit of water in the octanol or a tiny little bit of octanol in the water. There always will be, because these things are in equilibrium. But largely I have a proportion which is octanol and a proportion which is water. And we call this being immiscible. So when we say two liquids are immiscible, that means that they do not mix at all ratios. They might mix if I just have a tiny proportion, 1 in a billion octanol molecules for every water molecule. They might mix at that, but if I have a 50-50 mix, they don't mix. And that's what we mean by immiscible. So I'm going to take the fact that these two liquids have slightly different properties. One has much more hydrophobic properties, one is very hydrophilic. And I'm going to take a molecule which has multiple different types of bonding available in it. And that molecule is curcumin. Now, this is the structure of curcumin here. It has a keto-enol form, and here I've shown the enol. But either way, what we have is we have a couple of aromatic groups, some conjugation, which gives us some nice pi bonding. The pi bonding is very, very good at having induced dipoles in it. And so I have pretty good London dispersion forces. I've got 194 electrons. I get pretty strong London dispersion forces. And these London dispersion forces are largely my hydrophobic interactions. Now, my hydrophobic interactions mean that curcumin likes to dissolve in octanol. But we can also see there are bits about curcumin that might make it want to dissolve in water. So we have quite a lot of hydrogen bonding opportunities. We've got some alcohol groups, phenol groups, and we've also got some ether groups we can see hanging off there as well. And so these all have dipoles associated with them, and when something has dipoles, it's more likely to want to dissolve in water. And so we find that curcumin will dissolve in most solvents. But how well it dissolves in the solvents is what we're interested in this experiment. So I have a different amount of curcumin in one layer than in the other layer. And I can measure the concentration of curcumin in each layer. Now, to do this in this experiment, we're using something called the Beer-Lambert law. And the Beer-Lambert law makes the most of the fact that curcumin is coloured, it's yellow. And so part of the experiment is for us to determine a good wavelength for curcumin absorbing, and then to work out just how much light curcumin is absorbing at that wavelength. And we can calibrate this, and therefore I can work out what the curcumin concentration is in my unknown sample. And the Beer-Lambert law is saying that the amount of absorption in my sample is directly proportional to the concentration of my chromophore, of my curcumin. Now, if I increase the concentration, I increase the amount of absorption and I decrease the amount of light that passes through. Now, if I think about this overall, what I'm doing is I'm looking at how much curcumin is in my octanol layer, and hopefully you will also be able to look at how much curcumin is in your aqueous layer. And we can therefore work out what the equilibrium constant between those two layers are. Now, this experiment is fairly open-ended in terms of I've set you a relatively simple task. We're going to work out an equilibrium constant. But if we think about that structure of curcumin, we also have the ability to have functional groups be Lewis bases, electron pair donors. And so if we are in acidic solution, we might be able to make the curcumin be charged, take on that positive charge. Alternatively, if we're in basic solution, we have groups which are acidic. We could lose a proton and again give it a charge, which can affect how much it will dissolve in water. If it's charged, it won't want to be in the hydrophobic environment of the octanol. Now, to take this a little bit further, this might also affect the absorption spectra. We can't take for granted that just because its maximum wavelength of absorption in octanol is one wavelength, it will be the same in water. And so we can look at how these things are affected and just take that experiment that little bit further and allow your curiosity to kind of take free rein. Hope this introduces the experiment for you, but you can ask me questions in the lab if it doesn't.